Today I was learning about chemistry. This one was personally one of my favorites. First, we'll go over the topic of the strong nuclear force. Just like a magnet, protons that have a positive charge and electrons with a negative charge will attract each other. However, two protons or two positives will repel each other. The same with two neutrons, they'll repel each other. So how is it that these protons and neutrons could hold each other together? This force is called the electrostatic force. The amount of force, repelling force, of the electrostatic force is about 20 pounds, which doesn't seem like much, but on the atomic level, that's a lot of energy. If hypothetically, a proton would have been ejected from the electrostatic force, it would travel around 8,000 miles per second. So there's an incredible amount of force, electrostatic force and repulsion. So there must be an even stronger force that holds it together, despite the opposing force of the electrostatic. And that force is the strong nuclear force, which is said to be the strongest force in nature. The strong nuclear force counteracts this repulsion. The strong nuclear force is 100 times stronger than the electrostatic force, which is why it holds together. There is a property of strong nuclear force where the force only applies when protons touch or make contact or come very close. If they're not extremely close or touching, the force is zero, as opposed to electrostatic force, which can have a force pulling or pushing from a distance. Through a mechanism involving the exchange of subatomic particles called mesons at a very short distance, within the nucleus binding protons and neutrons together, the constant exchange creates the bind between protons and neutrons. Protons emit a meson, which is then absorbed by a neutron, and vice versa. This continuous exchange of mesons creates the attractive force that binds the nucleus. So why do mesons move? They are subatomic particles made up of a quark and an antiquark, which are bound together by the strong force, causing them to have inherent energy and momentum leading to motion. They are constantly exchanging this energy with their surrounding environment, resulting in movement. A proton is made up of two up quarks and one down quark, while a neutron is composed of one up quark and two down quarks. When a meson is exchanged, it essentially represents a temporary change in the quark composition of the particles involved. Quarks are indivisible, meaning they can't be broken down into smaller parts. Quarks are the building blocks of all matter. Quarks have a fractional electric charge, such as a positive, which is 2/3 of a positive, and that's for the up quark, and the down quark has a negative 1/3 of a charge. Quarks are assigned colors such as red, green, and blue to represent a property that gives rise to the strong force. Quarks combine to form hadrons, such as protons and neutrons, which make up the nuclei of the atom. The charge of a proton or a neutron are the sums of their quark charges. There are 6 types of quarks known as flavors. There are up quarks, down quarks, strange quarks, charm quarks, bottom quarks, and top quarks. But we're going to be mostly focusing on up and down quarks. As mentioned before, the up quark is 2/3 of a charge of an electron. A down quark is 1/3. Negative 1/3 of an electron of a charge. Up and down quarks have different masses and spin. The up and down quark are the most common. A proton, as said before, has one down quark and two up quarks, and a proton has a +1 charge. Considering that, the quarks give the charge of 2 ups and 1 down quark. So plus 2/3 plus positive 2/3 minus 1/3 ends up being equivalent to just 1. So it gives it a charge of +1. And with a neutron, two down quarks and an up quark gives the sum of 0, which is why it has a neutral charge. A antiquark is a quark with opposite properties. An antiquark has a baron number of -1/3, while quarks have a baron of +1/3. The baron, or byron, is a particle made of 3 quarks like protons and neutrons. Nuclear decay is the process by which an unstable nucleus loses energy by radiation. Radioactive decay occurs when an atomic nucleus is unstable and breaks down into smaller, more stable fragments. An unstable nucleus can be caused by an imbalance of protons and neutrons. For example, too many protons can destabilize the nucleus due to the electrostatic repulsion. Radiation, as the nucleus attempts to become stable, it emits radiation and loses protons, changing the element. The strong nuclear force is what determines if a nuclei of an atom is stable, giving sufficient energy to hold the protons and neutrons. An unsteady nuclei has too many protons or too many neutrons, or more protons than neutrons. There is a meson that emits, which attracts the neutron to the proton and vice versa. But if there are more protons emitting mesons to the insufficient number of neutrons, those neutrons will receive no mesons, thus losing its strong nuclear force between them. Thus, the proton or neutron is rejected out, and this is radioactive decay, which emits a radiation. There are 3 types of decay: alpha decay, beta decay, and beta plus decay. Alpha decay is the loss of an alpha particle, which is made up of 2 protons and 2 neutrons, with a mass of 4 and the charge of +2. When an alpha particle is lost, the mass decreases by 4 and the atomic number decreases by 2, changing the element. It changes the element by 2 on the periodic table. Beta decay is when an isotope has too many neutrons. A neutron turns into a proton and an electron. The proton is retained by the atom, and the electron is lost. The neutron turns to a proton because one of the down quarks within the neutron changes into an up quark, resulting in a positively charged proton while conserving the overall charge by creating an electron. The emission of a negatively charged electron balances the positive charge gained when the neutron becomes a proton. During this process, an electron is ejected from the nucleus. By losing a neutron and gaining a proton, the mass of the atom is the same, but the atomic number increases by 1. When an isotope with too many protons, the neutrons, it decays. This is beta plus decay. A proton converts to a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge, where instead of electrons being negatively charged, it's positive, or E+. The element is determined by the number of protons in the nucleus of an atom. The number of protons represents the atomic number. Hydrogen is 1 proton, thus the atomic number of a hydrogen is 1. 2 protons is helium, etc. Now we'll be talking about chemical bonds. A chemical bond, the force that holds atoms together in a compound, is called a chemical bond, which can be ionic, electrical, or electron transferring, or covalent, electron sharing, depending on the elements involved. When 2 or more elements chemically combine through a chemical reaction, with their atoms bonding together to create a new substance with unique properties, held together by chemical bonds like ionic or covalent bonds. A ionic bond is when 1 or more electrons are transferred from one atom to another, creating oppositely charged ions that attract each other. A covalent bond is a strong directional chemical bond that occurs when atoms share 1 or more pairs of valence electrons. Atoms covalently bond to gain stability by filling their outermost electron shell, or valence shell, For example, oxygen has 6 valence electrons and can bond with 2 hydrogen atoms, each with 1. Electronegativity is the measure of an atom's ability to attract an electron. It happens because atoms are more stable when their outermost electron shells are full. The more protons an atom has, the more it attracts an electron. Bit of a typo, but the more electrons an atom has, the farther away the valence electrons are from the nucleus. This means they experience less of a positive charge of the protons since it's further away. The electronegativity number is the value assigned to an element on the periodic table that represents its ability to attract electrons on the periodic table. That represents its ability to attract electrons on a chemical bond. A higher electronegativity number means an element has a greater tendency to attract electrons in a bond. To determine the electronegativity difference between two atoms, subtract the electronegativity from the electronegativity of the second atom. For example, the electronegativity of oxygen is 3.5 and 2.1 for hydrogen. So 3.5 minus 2.1 is 1.4. So the electronegativity difference between oxygen and hydrogen is 1.4. A ionic bond can form if the electronegativity difference is greater than 1.7. For a bond to be considered covalent, the two atoms should have an electronegativity difference of less than 0.4. If the electronegativity difference, I'm having a hard time with that word, is not high enough for ionization, but more than 0.4, the atom with the higher electron negativity will hold the electron more than the other atom. This is called a polar covalent bond. The more electron-negative atom in a polar covalent bond pulls the electron density towards itself. Due to the axis of electron, the atom is partially negative. The atom that is being pulled away is partially deficient of electrons and is partially positive. The atom with the electron closer than the second atom is the partially negative atom. Based on this diagram, you could see that the chlorine, the blue atom on the right, and the hydrogen atom are both sharing the same electron, which is keeping them at a bond. But the electron is closer to the chlorine than it is the hydrogen. Since electrons give a negative charge, chlorine has a slightly negative charge since the electron is closer to it, and a slight positive charge for the hydrogen since it's farther away from the electron. If the electron negative difference is less than 0.5, it is a nonpolar covalent bond. A nonpolar covalent bond, the electrons are shared evenly, give or take. And if it's two atoms of the same element, it's perfectly even. Now I'm learning about the different states of matter, such as gas, liquid, and solids. The primary factor whether a substance is a gas, liquid, or solid is the degree of movement and space between its particles. Atoms with much space between them can move freely in space, like most gases. Liquids are particles closer together, close enough for the particles to give the substance shape, but enough space between them for objects to pass through liquid due to the axis space allowing particles to move out of the way when in collision with the substance, while maintaining volume around the substance going through it. A solid is particles that are tightly packed together to where substances or objects cannot pass through due to much less space. Due to the particles being condensed together, there's a lot less space for particles or atoms to move out of the way, and it retains its volume and shape definitely. However, small particles that is smaller than the gaps between the atoms of a solid can pass through if small enough. What causes certain elements to have a certain number of electrons? The number of protons determines the number of electrons since the positive charge of the protons attract the negative charged electrons. The number of protons determines the element. 1 proton equals 2 hydrogen, and hydrogen can hold 1 electron. 2 protons is helium, and 2 protons can attract 2 electrons. 8 protons is oxygen, can carry 8 electrons as the maximum amount. Anything past that is at a neutral state, or past it's a neutral state, I should say. At the neutral state, which is when the electrons is the same amount as the protons, the atom has no charge, thus no longer attracts electrons. So in this diagram, you have 17 protons, 17 neutrons, and 17 electrons. Protons being red, neutrons being blue, and electrons being yellow, giving it a stable or neutral charge. And with its proton count being 17, that gives it the element of chlorine. This is Bohr's model of the chlorine atom. Here is the inside of a proton and a neutron, proton being red, neutron being blue. And inside of each proton and neutron, you have quarks. The 2 up quarks in the proton, represented by green, and the 1 down quark gives it a charge of +1. And on the neutron, it has 1 up quark and 2 down quarks, which gives it a net charge of 0. And here is a sodium ion. It is an ion due to the atom having more electrons than protons, thus giving it a negative charge. The element of sodium has 11 protons, thus 11 neutrons, and an extra electron, giving it the negative ion state. With the chlorine, it has 17 protons and 16 electrons, giving it a positive charge since there's more protons than electrons. And based on the electronegativity number of these 2 elements would determine the type of bond that these 2 elements will have, since there will be an attraction since one is negative and the other one is a positive ion. So since the chlorine has a positive charge and the sodium has a negative charge, it gives up its electron to the chlorine, now giving it more electrons than protons in the chlorine atom, turning the chlorine from a positive to a negative ion, and the same but vice versa for the sodium ion, since it lost an electron. This creates an electrostatic attraction, which then creates an ionic bond between the 2 elements. And 1 chlorine atom bonding with a sodium atom creates table salt. The ionic bond is formed when the negative sodium ion's electrons are attracted by the positive charged chlorine atom. Basically what I kind of went over, just I wrote it down, so it's kind of read it at your own pace. At the bottom right is the structure of salt, sodium chloride, and how they bond together. Chlorine being the green and the sodium being the white. It's a nice visual representation of how they compound together. And we'll get more into that and into how that works in the next chemistry session, because that'll be a whole different field. Now we're going to be going over the next element, H2O. Here's an example of an oxygen atom and a hydrogen atom. As you can tell, the oxygen atom has a full valence shells. However, due to the electronegativity difference, it will determine what type of bond it is. And in this case, it's a covalent bond, which is where both atoms share 2 of the same electrons. As you can see, this type of covalent bond is a polar covalent bond, which is determined by the electronegativity number, which determines what type of bond it is. The hydrogen and oxygen share 2 electrons, and these pairing or sharing, kind of rhymed, is what makes these atoms bond together as one, creating water. Here's an example of polar covalent bond of a water molecule, H2O, as shown in example 1. On example 2, notice the blue line that represents the distance between the nucleus to the shared electron. Notice the electrons that oxygen and hydrogen share has a shared electron closer to the oxygen atom than the hydrogen. The shared electron is closer to the oxygen, giving it a partially negative charge, represented by this symbol, symbol. The shared electron with the hydrogen is further away, giving the oxygen a slight positive charge. Now I'm learning about the periodic table and what all the symbols mean. I want you to note the noble gases, which is on the right side of the table in the blue, which are 6 noble gases, is what they're called. And there is a utility to them that I'll get to here briefly. So here is the element of carbon. The atomic number at the top left is 6, representing the amount of protons in that element. Remember, it's protons that determines what element it is, so it's the 6th proton that creates carbon. And there's the symbol, which is represented by C, and the name right below it, carbon. The atomic weight is the mass of this atom, being that if it's a neutral atom with full valence shells, it would have 6 protons and 6 neutrons, giving it 12. And there's also decimals for other variables. And now we'll get to the electron config. And also up above also describes the atomic mass if you want to read it. But the electric config describes the electron arrangement around a nucleus distributed among its subshells, the number of the electrons on each orbital shell. The first orbit or shell carries 2 electrons, the second shell holds 8 electrons, the third holds 18, the fourth holds 32, the fifth holds 50, the sixth holds 72, and the seventh holds 98 electrons. The amount of protons determine the max amount of electrons, so that means one proton can hold 1 electron. So if you have carbon with the atomic number of 6 protons, it could hold 6 electrons before filling out its outermost shell, the valence shell. So if carbon holds 6 electrons, it will hold 2 in the first shell, filling the first valence shell, and then 4 in its second shell, which makes the proton and electron count the same, making the last valence shell full. Electrons occupy orbitals with the lowest energy first within the sequence, being 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4p, 5d, 6p, 7s, 5f, 6d, and 7p. Now that sounds really confusing, but it'll all make sense here in a moment, hopefully. Each energy level is divided into subshells, denoted in S, P, D, and F, which can hold 2, 6, 10, and 14 respectively, that being electrons. The superscript number following each subshell indicates the number of electrons occupying that orbital. Here's an example. Hydrogen is 1s1, helium is 1s2, lithium is a little more complex because there's a shortcut that I have yet to teach you. But that's kind of the basics of it, and I will get to the shortcut briefly. So here is a electron config chart, part 2. On the right there, in blue, it shows the chart. There's, on the first row, it's 1s, 2s, and 3s. So the S rank is equivalent to 2 electrons. The P rank is equivalent to 6, and the D rank is 10 electrons. And you can see there's 3 rows. First row is 1s, and then second row is 2s, and then 2p, and then 3s, 3p, 3d, and it goes in that order. That's how the config works for the electrons. So both S1, S2, and S3 are equivalent to 2 electrons. 1p, 2p, and 3p are all equivalent to 6. So carbon has 6 electrons. So if you're going to interpret that through the config, you do the first one in order, 1s, that holds 2 electrons, and that will be 1s2, meaning you take all 2 electrons on the first rank of 1s. And you go down to 2s, and you also take 2. Now we're at a total of 4 electrons. And then you go to 2p, which is 6 electrons, but we only need 2 more to get 6 electrons in total for the carbon. So you'd only take 2 out of the 6 out of the 2p config. So the config would be 1s2, 2s2, and 2p2, giving it a total of 6 electrons. So looking at the chart again, the electric config on the right side there, we're going to find the config of aluminum has 13 electrons. So we just go down that chart, starting at the top, make it to where we reach 13 electrons. So we take 1s2, remember the S rank gives you 2 electrons, so you will take 2 of those. 2 more of 2s2, and for 2p we'll take 6. So we have 10 electrons so far. Then for 3s we take 2, giving us 12 in total electrons. Then for 3d we just take 1 to give us 13, 1 out of 10 in that rank. So the electron config of aluminum is 1s2, 2s2, 2p6, 3s2, and 3d1. So now on the chart, we're going to be learning about ionized energy and what that means. Ionized energy is the energy required to remove the most loosely bound electron of an isolated gaseous atom, positive ions, or molecule. It's the minimum amount of energy needed to remove an electron from an atom or ion. And how tightly bound the electrons are. Ionization energy is used to measure in kilojoules per mole, or kg-mole. Now we're going to learn about nuclear charge, because it pertains to what we're learning. The more protons, the higher the nuclear charge. The higher the nuclear charge, the stronger the nucleus attracts and holds the electron, requiring more energy to remove one. Also, the distance the electron from the nucleus determines the strength of the attraction. The closer the electron is to the nucleus, the more energy is required to move it. So an electron on the first shell has a stronger attraction than an electron on the third shell or orbit. An atom with a low ionized energy is most likely to lose an electron to a high ionized atom. And a high ionized atom is more likely to take an electron from a low ionized atom. And then for the state, it just determines if it's a gas, liquid, or solid. Carbon is a solid. Electronegativity, we went over that. There's the atomic radius, which is the average distance from the center of it. The average distance from the center of an atom's nucleus to its outermost shell measured in picometers. And then there's the crystal structure, which is I'm going to go briefly over that, but that's going to be on our next chemistry lesson where we go into it more detail, where I'm learning, because I'm still learning about it. Crystal atom structure refers to the specific repeating arrangement of atoms, where atoms are positioned at fixed points in a three-dimensional lattice, forming a highly ordered pattern. The arrangement is often described as a unit cell, which represents the basic repeating unit of a crystal structure. The lattice is the underlying framework of a crystal consisting of points in space where atoms are located, forming a repeating pattern. And here are some notes that I wrote down so you could just read at any time kind of what we went over. Continuing on, crystal structures. Crystal atom structure refers to the specific repeating arrangement of atoms where atoms are positioned at fixed points in a three-dimensional lattice, forming a highly ordered pattern. The arrangement is often described as a unit cell, which represents the basic repeating unit of a crystal structure. A lattice is the underlying framework of a crystal consisting of points in space where atoms are located, forming a repeating pattern. Kind of already went over that. But lattice formation, the lattice of an atom is primarily determined by the size of the ions, the ratio of positive to negative ions, And the arrangement of atoms within a crystal structure is dictated by the need of minimized potential energy by optimizing the packing of ions based on their size and charge. The coordination number is the number of the nearest neighbors an ion has in the lattice, which is influenced by the relative sizes of ions. Here is what I'm still in the process of learning, the coordination. There's a simple cubic unit cell at the top left. V equals the volume, meaning 52% of the volume is empty space, filled. There's body center, which has the volume of 68% full of atoms, and that's with the atom in the center of the cube lattice. And then the face center, which takes up 74% and has 6 atoms in the center of the cube lattice. The coordination number of atoms that attach to a single atom in a cubic structure is attached to an adjacent to 6 other atoms. R equals the width of the unit, R2 is the height, and X is the depth of the unit cell. Now we're going to do the electron config, but a shortcut, which is also called the noble gas shortcut. Noble gases have full shells, so they don't give or take electrons and can use them as a starting point for the electron config, starting at one of the noble gases, starting at the noble gas above the element we want to config for. So the first step is to find the preceding noble gas before the element. For example, the config of sulfur has 16 electrons, and it is in the p block. As you can see, each block of element tells you which config it is. On the left is your S blocks. The yellow in the middle are your D blocks. The right is your P. And the bottom are your Fs. So again, the example, config of sulfur has 16 electrons, is in the P block. So that's where you start. And it's in the third row, so it's 3P in the fourth element. So you look at the noble gas and see which noble gas is above sulfur, which in this case it's neon. So to start the neon config shortcut, you start with neon, Ne. To find sulfur config, which has 16 electrons, is in the P block, so that we're starting at P, in the fourth element on P4. We already established neon is the prior noble gas, so we're going to use neon. Neon has 10 electrons starting with. So in other words, made a shortcut by starting with 10 electrons when we write down neon, Ne, then plus when we're going to add the other configs to complete it. And I wrote down in pink the different columns. So starting back at sulfur with neon as its base, giving us 10 electrons, we go to the next one, which is 3s, or S3, which is 2 electrons, which brings it to 12. And then P3, just going down the chart, we're at P3 now. And P holds 6 electrons. Since we already have 12, all we need is 4. So it'll be P34. So the noble gas shortcut for sulfur would be neon plus S32 and P34, giving us 16 electrons, which is the amount of electrons sulfur has. So that's the noble gas shortcut. Then I took 3 tests, 25 questions each, 75 questions total, and did pretty well. I was happy with it. I missed one in every single one of them, except for the last one, which really sucked. I really wanted that 100%. But I was happy about the results, and I think I did pretty decent. So thanks for watching if you made it this far, and look forward to posting the next video. Hope it was helpful.